In this lecture, we will start looking at mismatch, more specifically at a particular type of mismatch called systematic mismatch. So broadly, we first need to find out what mismatch means. Now, if you look at traditional analog design, discrete analog design, not in integrated circuits, it's very rare that you would find people talking about mismatch. Whereas on integrated circuits, pretty much, almost all the time, you will be interested in what mismatch is and how it is going to affect your circuit. The reason is very simple. So the origin of study of mismatch comes about because on ICs, we assume that devices with the same parameters are identical. What do I mean by this? Suppose I take two transistors on an IC and I make sure they have the same geometric parameters, same width and same length. I am automatically going to assume that these two devices are going to be identical. In other words, I apply a gate source voltage, DC gate source voltage on both the devices. I should get exactly the same current to as much accuracy as I care to observe. However, having said that, what happens in reality is that these devices are only nominally identical. What do I mean by nominally identical? So what this means is that these devices will be very close to each other, but there will be some small differences, and a lot of analog design assumes that you're going to try to make these devices as identical as possible, and hopefully by the end of this course you will be able to appreciate why this is such a strong advantage of IC design. So the minute you say that if you take two devices, they are only nominally identical, it means that there is some amount of mismatch between these two devices, two or more devices. So therefore, we now identify two sources of mismatch. The first type of mismatch is what is called systematic mismatch. This is the type of mismatch that we will study in this class. And in the next class, we will study the other type of mismatch, which is called random mismatch. Now, let us look at systematic mismatch in a little bit more detail. So we will actually take an example. So let us say I am trying to build a resistor. Why would I want to build a resistor? I may want to build a resistor because I am building an amplifier, and to build an amplifier using a negative feedback circuit, let us say I am trying to build an amplifier of gain -2, and I need two resistors for this, and I need a resistor R and a resistor 2R to create this amplifier. The gain of this amplifier, of course, is -2. Now, what do I assume when I do this? I assume that I can build the op amp, and hopefully by the end of this course you will be able to do this. And you should also be able to decide what type of resistor you need and what is the size of the resistor, value of the resistor, etc. But let us look at it first from let us look at the resistors for now, because that's an easier thing to understand right now. First of all, if you take an integrated circuit, there are many different types of resistors. So now obviously these two resistors, now I'll call them R1 and R2. I want R1 and R2 to be matched first of all, and more importantly, I am assuming that R2 is exactly equal to twice of R1. So therefore, the first thing I need to note is that R1 and R2 need to be the same type of resistor. What do I mean by this? It turns out on an integrated circuit, you have several different types of resistors made using the different materials available to you. For example, you can take an N plus or a P plus diffusion, which is basically just a piece of doped material, and make contacts on either side, and that could be your resistor. You could take a piece of polysilicon, you could take a piece of metal, etc. And then there are really maybe 4 or 5 or maybe even larger number of resistors. Obviously, the characteristics of these two resistors will be highly variable. One type of resistor may have a completely different temperature coefficient from the other one. It may have a different linearity behavior, and so on and so forth. And therefore, it is extremely important that you make R1 and R2 be the same type of resistor. Now, this is like the 0th order of mismatch understanding we need to have before we start looking at this in a little bit more detail. Now let us say we choose the diffusion resistor. Let us go to the next page. So let us say I am going to build R1. I am going to take a piece of diffusion, right, and some, let's say, N plus diffusion, and now I need to make a contact. I need to connect this resistor to the rest of the circuit. So I am going to put in what is called a contact, which allows you to connect a metal wire or a metal layer to this particular resistor. Let's say I'm going to show that using the blue color. So this blue color is the metal wire that I am using to connect the resistor to the rest of the circuit. Now how would I build R2? So now first I need to note that this diffusion is going to have some conductivity, right, and it has a certain length and a certain width, right, and knowing the conductivity and the knowing the resistivity, the L and W, I can say that the resistance is going to be rho L by the cross sectional area A. I should note that if current flows, there is some thickness T for this particular diffusion when the current is flowing in this direction. Now I want to make a resistance of value 2R. So of course the first thing that I would try to do is to build a piece of diffusion that is twice as long. So 2L, I would use the same width and of course the same thickness, which you normally do not have control over, and use the same type of material so that you have the same rho. And this is R1, this is R. R2 should ideally be rho into 2L by A, and this should be 2R. This is the nominal value that you will get. Now unfortunately, it turns out that there are some other aspects to take care of. So first of all, the resistors that you connect to the rest of the circuit, you need the metal wire and the contact. So let us assume that the metal wire is ideal for this purpose. In reality, that may also affect your design. Let us say it is the contact that has some resistance small r. So the contact has a resistance small r, and I'm going to call that the contact resistance. So the actual value of R1 is actually equal to R plus 2 small r. Now let us look at the 2R resistor, which is R2. Now that will also have two contacts, and it is going to be connected using the same metal wire in blue. What is the actual value of R2? It turns out the actual value of R2 is not just 2R, it is 2R plus to small r. Now remember, what do we actually want? We are not specifically in this particular application, we do not care about the value of the exact value of R1. Even if it varies by a little bit, it may not affect your amplifier in a very big way, but the ratio of R2 to R1 matters in a very big way. So what we want is, we want R2 by R1 to be equal to 2 exactly. It turns out, in this case, actual R2 by R1 is 2R plus 2R by R plus 2R. This of course is going to be slightly less than 2, clearly. Now how do we fix this problem? Of course, if the actual error depends on the relative values of capital R and small r. But you can imagine that there will be cases where this difference, this error will matter. So now the best way of fixing this problem is to first figure out what we want. Let us assume that we cannot remove the contact resistance completely. So what we actually want is R2 should be equal to 2R. We want R2 to be 2R1, which is actually 2R plus 4 small r. In other words, the way we should build R2 is not just one single large piece of wire, but a single large piece of diffusion. We actually need to put in two pieces of R1, two pieces that are identical to R1. And in this reminder that in this particular case we are assuming that the metal has no resistance, and if you build R2 in this manner, then the value of, in this case, R2 will be equal to 2R plus 4 small r, and this will give you exactly twice of R1. This is actually a very simple, almost trivial example for people experienced in analog design, but I just kind of wanted to show you how small changes in the way you build and use these kind of components can make big differences in your actual circuit design. Obviously now you can extend, you can imagine that such small changes can be extended for other types of resistors, for other types of components, and so on. Let us look at one more example. Let us say you are trying to build some circuit where you need two capacitors to be identical. So in other words, this was in a case where you wanted one resistor to be twice the other. Let us say this is example number 1. So this is example number 1, and my next circuit is going to be example number 2. I want to create capacitors C1 and C2 that are exactly equal to C. So the way you build the capacitor is probably using two parallel plate capacitances. Let us say I have these two parallel plates, and on a different metal layer I draw out two plates, and I get my two capacitors. I get a capacitance between these two plates. So this is node 1 and node 2. Now I can make a copy of this and call that C2. So let us say I make a copy of this and I call it C2. So this is C1 and this is C1 and this is C2. But now let us assume that next to one of the capacitors there is actually a metal line running on the same metal layer, and I'm going to show that this is some metal line. Let us say this was at ground potential. What is going to happen is that this capacitance, these metal layers, in fact I should actually show you the top view before you can understand this, so maybe I'll move to the top view on the next page. So let us say this is the top view of the two capacitors. And let us say I have a metal line running next to one of them, which is grounded. So I'll just show it as a single line. And this line happens to be grounded. What is going to happen is that there is going to be some fringing cap between C1 and this metal line. So if you actually look at this, the equivalent circuit of C1 between nodes 1 and 2, you are going to have a capacitance C, but you are also going to have a capacitance C fringe between node 1 and ground. Whereas C2 is going to look exactly like this. Now let us assume that between nodes 1 and 2 you want C1 and C2 to be completely identical. What you should be going in and doing is to put in a grounded metal line next to C2 also at the same distance D, so that C2 also has a C fringe between its nodes 1 and ground. This will make sure that C1 and C2 are identical in all respects. So now you can see I can now extend it to all different kinds of structures. Let us take a third example. I am going to take a third example. Let us say I want to build the same capacitor. I used a width W and a length L for the plates. Remember that the capacitance is epsilon A by the distance between the plates, where A is W times L. Just a reminder that we are still dealing with the top view of the capacitor. Now this is C1. Let us say somebody decides to build C2 in this manner. Let us say somebody decides to build C2 in this manner. Now nominally it will look like the capacitance is epsilon A by D, but first of all any capacitor that you build will always have fringing capacitances to any ground line however far away it is. And what you will find, if you take into account all the non-ideal effects, you will find that C1 is equal to C2 nominally, but these capacitors will behave very differently with respect to very differently when they are used in a circuit. Now so you should always build these kinds of circuits such that so you should always build these circuits such that you have the same aspect ratio. So you should not be building C2 like this. So you should build C2 such that you have the same width and length, and this is the correct way of building this capacitor. I can go on with other examples, so maybe we will take one more example before we summarize our understandings. So let us take a MOSFET. and I'm not going to draw the layout, but the schematic, I mean the circuit, just drawing the MOSFET symbol itself and drawing out the parameters will be good enough to for you to appreciate this difference. So suppose I want to take two MOSFETs and make sure that they are identical. So this is M1, this is M2. Let us say that you apply a certain bias voltage, you want them to have the same bias current. Let us say that this MOSFET has a width L, width W and a length L. Of course, you want to make sure that this transistor also has the same width and length. We know that if you just look at the bias current in the saturation region, we know that the dependence of the current on the voltage is quadratic. Now clearly this equation tells you that the current is proportional to the ratio of the width and length. So you may think that this is exactly the same as using twice the width and twice the length, or half the width and half the length, but that is completely incorrect. You will find that you should be using the same width and the same length for these types of transistors. That is because there are always second order dependencies of the current on other parameters which will depend on the actual values of width and length. For example, we are ignoring the dependence on drain source voltage due to channel length modulation. It turns out that lambda itself is a function of the width and length, but in different ways, which means if you use a device with twice the length and twice the width, its lambda would be completely different from the original device. So let us now summarize our understanding. So if you need to have two devices or two or more devices that need to be perfectly matched, the way you would summarize these findings is that they need to have the same geometric parameters. So when I say the same geometric parameters, what I mean is if they have a certain width, a certain length, a certain thickness, certain distances, etc., all of those should be kept identical across the multiple devices that you want to be very well matched. And if I want a larger or smaller multiplication, so I need to make sure that I use multiples instead of a single large device. So that example, that particular point is covered by the first resistor example that we took. We first tried a single larger device where we wanted R2 by R1 of 2, but then we found that what actually works is two devices which are identical to the first one, which are connected together. So use multiples instead of one single larger device. And the same will hold true even if you want to build a current mirror, for example, using MOSFETs. And you need to ensure that both devices have the same environment. What do I mean by environment? We saw in example 2 where you could have fringing capacitance. Because one device has a metal line next to it where the other one does not. You need to maintain the environment around the device to be identical. Finally, you need to ensure that these devices have the same orientation. This is because you really don't know when building the device whether there is some gradient in things like temperature in the foundry, doping concentrations, etc. So that is extremely important. And now this fifth one, Because there may be gradients across the IC, you want to place these devices close to each other. What I mean is that if you build the same circuit on one end of the die compared to the other end of the die, you could have completely different values of doping concentrations, mobilities, thickness, metal thicknesses, etc. So this is following these conditions is extremely important. Now, if you follow all of these, you will find that your systematic mismatch is reduced to a very large extent. In other words, you can think of systematic mismatch as something that is almost completely under the control of the designer. And there are some very simple techniques that you will routinely follow to take care of systematic mismatch.